A warm welcome to all dear participants and the dignitaries, and thanks for IEEE for giving me an opportunity to present the topic on optimal placement of EV charging stations in utility grid, which is a case study of Kerala State Highway Network we have done. The work was done jointly with Energy Management Center and College of Engineering Trivandrum, and thanks for my guide Dr. Harikumar sir for his valuable guidance for achieving this work. So coming to the presentation outline, so we'll be seeing the methodology, how it will be implemented, and how what is the transport network, how it is formed, and the superimposition with utility network, what optimization technique is used, and it is basically an optimization program. And we'll be studying the siting and sizing of EVCS, and the load flow analysis will be made to validate the results, and we will be studying the case study of Kerala State Highway Network, how it is applied, and we will conclude in the topic. So coming to the introduction, so government of India is very much keen in the EV technology, the implementation of EV. Throughout 100% EV, it is promoted by the government by 2030, and the National E-Mobility Plan and the FAME scheme. And throughout in Kerala, we have almost 4,539 EVs on road as on December 2021. This is a very large number, and we'll be expecting 1.39 lakhs EVs by the end of 2030. So this needs a huge EV infrastructure, EV charging infrastructure to enroute charging and reliability of the EV transportation. Now, coming to the this will be causing a great impact to the power grid, and it should be affecting the system stability if we is not integrating it suitably. So the grid security and other things will be affected. So the load generation balance should be properly ensured along with the renewable energy systems. Now, this is the methodology. We have identified the problem. We have done a literature survey, and we have reviewed the conventional and advanced optimization techniques which are used in these problems. And the route formation and superimposition of the networks were done. Optimal sizing and siting were done after applying genetic algorithm and simulating the results. Now, the load flow analysis we have done using a power system analysis software, and we have done a case study of the implementation of the technique in a Kerala state power system and the highway network. And the estimation of voltage drop and the power losses were done and analyzed. Now, this is the highway stretch, National Highway 66 stretch of Kerala state. So the entire this one network was considered from Thiruvananthapuram to Kasaragod, and we have certainly pointed out certain candidate locations for the shopping malls, supermarkets, this KCB substations, children's park, restaurants. So these are the probable candidates where we can place the charging stations. So this was properly coordinated through the Google map. And we have identified these charging stations at different types and different numbers and how much for each district. So where Alappuzha is the largest stretch in this, and we have identified these. This is one stretch from this near to one district in Kerala and near to So after that, we have identified the critical nodes, which are the where we have taken certain route trips from Trivandrum to Ernakulam, Ernakulam to Trivandrum, Trivandrum to Kasaragod. Different scheduled trips we have considered, and we have certain vehicles we have considered fit their certificate range, Hyundai Kona, Tata Nexon, and also we have arrived at certain points where we need to charge the vehicle critically. So these points are called as critical points. So critical nodes we can call for. So these critical nodes are represented in black color like this. These points, charging station should be there, should be mandatorily there. Other nodes are candidates, and these nodes are fixed, and these are critical. Other nodes are movable, and these should be optimized using a suitable optimization technique. Now we have superimposed this network using a standard IEEE 33 bus system for a testing purpose. So this is the test specimen for the study. So this is the problem, and we have the decision variables are the number of charging stations and the position of charging stations, and the objective functions are framed like the capital expenses, capex shall be minimized, and the operating cost opex shall be minimized, which is a product of power consumed by the charging station and the time and the operating cost. Now the losses, grid losses, which depends only on the voltages from sending and receiving end and the load angle difference, it should be also minimized. And these are the constraints, the active power limits of active and reactive power limits of the bus, and the voltage drop limits, the critical nodes, 52 nodes we have taken. So this should be placed, and the power generation, load generation balance should be maintained. Yeah. So this is the optimization algorithm. This is the block diagram representing the algorithm, and we will be selecting the test network. We will be putting the parameters. We will be setting the constraints. We will be performing optimization using a genetic algorithm-based technique is deployed here, and we will be arriving the location of charging stations, number, and the type. So the siting and sizing will be done, and we will be performing a backward and forward seep load flow analysis to suitably optimize this. Once the siting and sizing is done, this program is achieved. After that, we have placed this, and we have arrived the siting and sizing. Sizing is the load for each. These are the nodes where charging stations are placed, and these are the numbers which are placed, and the operating and capital cost are arrived, and this is the placement map, and this is the cost, the total load for each bus. So these are the statistics we have shown. Candidate nodes, critical nodes are already maintained. So this is we have done. So after that, we have validated the results by doing a load flow in the ETAP software was used for optimization. MATLAB software was used for validation using load flow. We have used ETAP software. So this is IEEE 33 bus system where we have placed the charging stations. These are green color. These are the charging stations placed at the nodes where we got the results. And now we got the branch losses, pre-placement and post-placement. We are comparing. So there we can see there is no much huge difference. There is no difference. There is a almost the same. There are no much losses. This is due to the optimal placement. If it is non-optimal placement, losses will be more after placement. This is the comparison of reactive power losses, branch losses, and this is the including the voltage deviation, voltage drop deviation, and all the reactive and active losses taken together for each bus. Now we have done the case study of the Kerala power system combined, superimposed with the Kerala utility grid. That is the KCB network. KCB is the utility network for us. This is a 27 bus 22 kV, 220 kV system. We have considered the voltage levels at 220 kV to avoid complication. If we come down to 110 or 66 kV, the number of nodes will increase. The problem will get more complicated. Due to the time limitations and all, we have limited to 220 kV system. So 27 buses are considered. So this data is prior to transcript upgradation of the KCB system. And yeah, so a part of the network is considered for study. So this is a placement map for Trivandrum, and this is a placement map for Kochi. A part is shown here since it is not viewable full scale. So the similar technique with the previous superimposition with the IEEE 33 bus system, and one part of the district was taken. Similarly, the optimization was done for the entire Kerala state highway network, and we got the we got the results, and we validated the results by simulating the load flow in similar manner. In the similar methodology was taken for this case study also, and we have simulated it in ETAP software. And this is a part of the grid. It is the northern grid of the 27 bus system. The full system is not viewable in this screen because it is very big. It is some buses we can see here. It is a northern grid of Kerala. So we have got this is the load distribution of the EV charging stations after placement in each bus. You can see the 27 buses from Tirunelveli to Kasaragod, starting from Parithipara substation to Manjeshwar substation. So this is the Kerala map showing the grid lines. So we got similar results we got for this case study also. Pre-placement and post-placement, the branch losses are not much affected, more than 2 to 3% maximum. So the placement is very optimal. This is an optimal placement. Then the reactive power losses also not much pretty affected. It is almost similar. The voltage drop also in some buses we exceeded 4%, but it is due to the loading. It is the maximal loading of these buses already with the KCB network. The KCB is all planning for the expansion of these networks nowadays. So that also it was a constraint, but the results are optimal. Now coming to the conclusion, for a reliable and long industry, for a EV owner like me, I own an EV, but the constraint for me is the long trips. For long trips, I think where the charging station will be there. So when the charging stations are placed, it should be giving me a suitable opportunity to attend a shopping mall or restaurant while the charging is done for 1 hour, what I will be doing. So this is the challenge. So this will be accommodating, and the optimal placement solves this problem. It is a combined problem for e-mobility planners and power system engineers. It is a planning as well as utility problem. So this work is discussed, which is highly relevant to optimize the revenue and operational expenses, user convenience. It is a multidisciplinary problem. So further adoption to the virtual power plants shall optimize both the charge-discharge coordination and the EVCS scope of attractive real-time pricing. So this comes with the advent of smart grids in future. So the modernization and equipping with the surplus DG sets, distribution generators like solar and wind from renewable energy, and the distributed loading from the e-mobility is a unpredictable and undispatchable load. Also, the renewable energy is also unpredictable and undispatchable source. So matching renewable energy and EV load shall be matched from source to load to in an optimal way, so that the grid expansion will be easy. So that the microgrids and nanogrids come in future, and the smart grids will be taking up the technology. So this is a multidisciplinary problem. It has got a lot of opportunity for improvement. In future, we are trying to incorporate this virtual power plants and the charge discharge coordination, real-time pricing, etc. in this work, and we are trying to extend this work to that level. So these are my references. There are a few references for this project. So these are mainly the S. Sanjay Dab and ma'am got a lot of papers. So these papers were mostly referred. So different optimization techniques were referred, and how this methodology, what methodology they have done. So we have also applied these, and we have done in a similar way in a novel fashion for the Kerala State Network, Kerala State Utility Network, the 27 bus system, and the highway NH66 network. So that's all from my side. So I thank IEEE once again for giving us an opportunity to present this topic and take it forward. Thank you.